Hello everyone, my name is Eusebio Rodriguez and I'm joined with my partner Suleiman.
Suleiman, Anaza.
And today we will be presenting a battery management system. And this is under the DOED research, MSEIP research. I'm in Scholars Academy and I'm a CIET major, Control Instrumentation Engineering Technology. And Suleiman.
I'm a chemistry major currently, and I have worked with Dr. Feng in the past, and I'm working with the studio now.
So, as an introduction, first we want to introduce what a BMS is. So, BMS is a battery management system, and here you can see a BMS built by Electronic Projects Hub, which is what we based our schematic for the BMS on. So, this BMS, we at first wanted to apply this BMS to lithium-ion batteries. And for lithium-ion batteries, we'll get into it later, they really need to be charged a specific way and discharged at a specific way too, which is what Suleiman will introduce in the next coming slides. So.
Sure.
Next, sorry.
So with the lithium-ion batteries, there's two main things that we that bring difficulties when charging lithium-ion batteries that aren't noticed, that you don't see with other battery chemistries. With lithium-ion batteries, they operate in a very narrow set of voltages, and outside of those voltages, you get quite a few issues. Like you will get plating formation, and it will lead to cell destruction. And you've probably seen online maybe a few batteries exploding. You can get situations like that from exiting this narrow range of voltages. An overcurrent also causes the gel barrier inside the batteries to decompose and also give you the same issue of uncontrolled reaction inside the battery. So with the BMS is trying to manage those two things. So if you could, sorry. A BMS's duties are to manage and regulate the current and voltage and to try and prevent cell failure while you're charging, right? It's also it also regulates temperature, because with uncontrolled temperature you can run into issues with thermal shutdown, which we'll talk about a bit more later in the actual nitty-gritty of the cell with the temperature and what do you call it, with multiple cells with multiple cells in a battery pack. You run the issue of cells back charging each other, so the BMS in differences in the BMS regulates the charging of each individual cell and allows them to work and communicate inside the battery pack. So
yeah, and as in the other slide that showed the Electronic Projects Hub schematic, it has multiple cells that you can charge with this BMS. So that's what he was explaining, that the BMS will be able to limit the overcurrent discharge and current charging.
So I'm going to talk a little bit about how the charging, how the BMS will regulate the charging application. In our BMS, with lithium-ion batteries, there's two phases to the charging. There's a constant voltage phase, and there's a constant current phase. Our BMS our BMS is regulating both. So using when lithium batteries are charged, they will charge to a specific voltage, 4.2 volts. That's the max charge voltage of a lithium-ion battery. And then it will have to rest at that voltage, but the current will have to decrease to reach a saturation charge, so you can get the full depth of charge in a battery. It's like you see in fast charging applications that you'll reach that critical voltage, but you won't have the full depth of charge because you're not doing the saturation phase. That's why our BMS has these two regimes. And then temperature. We're talking about temperature management. Temperature management is important because, as stated, once cells hit a certain point, the organic solvent that the lithium is dissolved in will break down and start an unstoppable reaction that will destroy the cell and may cause a cell explosion or a fire. So we use temperature sensors in our BMS to manage the cell to keep the cell within a safe range of temperatures, so that we can prevent the thermal runaway risk from occurring. All right.
So for lithium-ion batteries, as we said before, they need to be limited when charging. Like Suleiman was just saying, if you do too much current to charge them, then it will cause, as Suleiman said, a lot of issues with a battery explosion. The battery life itself could diminish. It can harm the cell deeply.
So with overcurrent situations, you run into the issues of when you start running into less of the actual electronic limit of the battery, you start running into more of a thermodynamic limit, where you're running too much current, but the cell's electrolyte cannot pass enough. You won't pass enough lithium ions to each side of the battery to sustain the amount of current you're pulling from the battery itself. So the reason we have this current limiting is so if there's a case of overdraw or overcurrent demand, we can limit and stop the load from destroying the batteries when causing a larger safety issue.
This is our current BMS design, inspired from the Electronic Projects Hub schematic. Here is just a more simplified version. We have the current voltage, constant voltage,
and
constant current regulation up here, and then down here is the actual 3-cell charger BMS. So with this software is actually the PSpice version 17.4. We had gone in contact with OrCAD and were able to get the trial version. And yeah, that's here.
We use PSpice to do so before we build the circuits in real life, we use it to do simulations so we can test our efficiency and our overall current draw, and make sure all these components are working in the way that we expect them to work. So it's been a very useful tool for lowering the cost of prototyping and designing the circuit. And we are so for our future research, because this is an ongoing research project, we plan to add microprocessor functions. So our current cell BMS works off of using diodes to dissipate power for the balancing function. We would like to replace that function with a more efficient cell-to-cell balancing function using a microprocessor similar to this Arduino that we have here. And as for future temperature control, we currently using just pure shutdown, more passive temperature control. We would like to add active conditioning to our BMS, using fans and heaters to stay in the ideal temperature range for lithium-ion batteries. And we're doing a bit more work on the current control using the microcontrollers, so we can have a more refined cell maintenance. To refine cell maintenance and keep the cells lasting longer. So, what's that? This are references.
Yeah. And then the next one is just thank you to Scholars Academy and Dewey, the MCI.
Our acknowledgements.
Yeah.
Any questions? Sorry.
Yeah, the next question.
Sorry.